there can be some clever algorithm which could solve for us the problem. And it turns out that currently there is no known algorithm which would find the minimal or the optimal Hamilton circuit fast in reasonable time which they would go would depend in some polynomial way on the number of vertices. So currently there is no known fast algorithm to solve the traveling salesman problem. And some people believe, although it's not proven, but some specialists believe that it's not possible to find such a fast algorithm. The problem just has a very high level of complexity. And it's interesting to note that, well, it looks like it's some kind of isolated special problem, traveling salesman problem, but it turns out there are lots of other problems in discrete mathematics which are linked to the traveling salesman problem. In the sense that if we had a fast algorithm to solve TSP, we would also have a fast algorithm to solve a whole bunch of other problems. So it sits in some class of problems, right? So if you learn how to solve fast one of them, you know how to solve all of them, although they're very different. So it has more significance than just this, traveling salesman problem per se as formulated. So what can one do if you don't have any algorithms which guarantee to find the optimum fast enough? And you can relax the conditions. For example, you can search for an approximate minimum. And with that, of course, you'd like to know how far off you might be. So suppose you find a Hamilton circuit, you don't know whether it's optimal or not, but it turns out you can estimate. You can say that, oh, this is probably not the optimal, but the error is not more than 1% or than 10%. So this is a different strategy. So you're looking for an approximate solution. And here, I think the current state of the art is that there is a fast algorithm, so polynomial time algorithm. The time depends polynomially on the number of vertices, which will find an approximate solution and guarantees the error to be slightly less than 50%. So that's sort of the current state of the art. And yet, people managed to solve the TSP problems for graphs with tens of thousands of vertices, right? So we discussed 50 vertices last time and brute force. So it's quite an achievement. In fact, there are competitions amongst teams of teams of different universities and different companies. So there's a challenge, for example, given a complete graph which represents, say, towns in Sweden with weights being distances between them, and you find the optimal Hamilton circuit. And so this type of challenges, and they have been successfully solved. So what is the most successful strategy? The most successful strategy is coming from two ways. One is to generate, construct some clever algorithms to generate candidates for the optimal circuit. So current best strategy has two parts. So first, generate hopefully good candidate circuit. And secondly, write other algorithms which would estimate how close your candidates are to the optimal. Generate bounds which tell you how close your candidate is to the optimum, or to the real minimum. And the third ingredient in this approach is luck, because none of these. So you generate candidates, but there is no guarantee that necessarily at some point you'll generate the absolute, the minimal circuit. Here also you try to estimate. So there are separate algorithms which estimate how close you can be to the minimum, and yet again there's no guarantee that you'll find the best estimate, right? So the estimates also have some error within them, and yet constantly modifying strategies in part one and strategies in part two, what people do in practice with some luck, they manage to solve huge TSP problems and to solve them exactly, to the point that you find the exact solution, not an approximate one, but you can prove that that's actually an exact solution. Okay, so third ingredient, with luck, not only approximate, but the true minimum circuit can be found. Okay, so I'm going today to discuss one strategy to generate good candidate circuits, and I will also discuss how one can use minimal spanning trees to generate the bounds, right? So I will demonstrate how these two strategies work, and it's the simplest sort of strategy which exists there, but that basically demonstrates how the whole thing is supposed to work, right? So I'll start with the following algorithm to generate candidates, which is called the nearest neighbor algorithm. So NNA generates candidate circuits. How does it do it? So it starts by, it selects the starting vertex, and then you travel along the edge with the smallest weight available to a vertex that has not been visited yet. So the second piece of instruction is travel along the edge with the smallest weight available to a vertex that has not been visited yet. Right, 3, repeat step 2 until all vertices are visited and you came back to the starting vertex. So repeat step 2 until all vertices are are visited, and you return to the starting vertex. Right. I will illustrate how it works on an example with which I'll be working more further. So please bear with me. It has 5 vertices. It's a complete graph with 5 vertices I have to draw now. So it looks like a pentagon, but then there are all sorts of diagonals in it. So from each vertex there should be 4 edges coming out. One, two, three, four. 1, 2, 3, 4. And the labels will be like this: A, B, C, E, and D. And I'll use the red color for the weights. So I'll put the weights next to the edges. So that's 7, 2, 3. One is 14. 1, 5, 12, 8, 4, 10. Okay, so that's a complete weighted graph with 5 vertices. You know them as K5, right? And the weights are given. So, we will use the nearest neighbor algorithm, NNA, starting with vertex A, and then starting with vertex B. So this will generate 2 different candidate circuits. So starting with A, so this is an algorithm which belongs to the class of greedy algorithms. So now I want to minimize the total length. So now each time I have a choice, I'll go for the smallest weight available. So I look at all the edges incident with A, namely AB, AC, AE, and AD, and I see the weights are 10, 14, 3, and 7. I take the one with weight 3, because that's the smallest weight available. So AC, and I record the weight, weight 3. From C, I can go to E, to D, or to B, right? I cannot go back to A just yet, so that should be the last edge. Before that, I need to. There's somebody laughing all the time, and I find that really distracting. Okay. So from C, you can go to E, to D, or to B, and again, you look at the weights. CE has weight 8. CD weight 12, and CB weight 2. So 2 is the smallest weight available, so we go to B next, and the weight is 2. So now we're in B, and now there are only, right, so there are 2 vertices not yet visited, D and E. So I can either go to D or to E. The weight for BD is 1, and for BE is 5. 1 is smaller, so being greedy, I go to D. And now there's only one vertex which has not been visited, so I have no choice. I have to go there, regardless of the weight, and then I must return to the starting point A. So in this algorithm, the last two edges are automatic, so you don't have to make any choice in there, right? You don't have to control. So we must go from D to E, that has weight 4, and from E to A, and that has weight 14. So 14 is a very large weight, but we have no control at this stage, right? Because we have exhausted our options just by following our grid, right? And we're forced to take this 14, the edge of weight 14 at the very end. So let's calculate the total weight. Here, 5, 6, 10, it's 24. So this candidate has weight 24. Let's do it one more time, now starting with the vertex P, and you'll see that in general, the path will be different, right? And weight can improve. So from B, our weights, the available weights are 1, 2, 5, or 7. So what is the smallest? So I go to D, weight 1. From D, I can go to A, to C, or to E, and the weights are 4, 12, and 10. 4 is the smallest. So I go to E. From E, I can go to A or to C, and the weight for C is smaller, that's 8. And now, the only unvisited vertex yet is the vertex A, so I must go to A, and CA has weight 3, and from A I must return to B. AB has weight 7. So this gives us the total weight of 5 plus 8 plus 3 plus 7, so that's 23. So that's better than the previous one. And in principle, you can run this algorithm from each vertex in the graph and then select the smallest weight circuit and then think that that's your best candidate. But you don't know yet, you know what's the optimal solution. That might be very far from it, it might be very close. So this answer will be partially answered. We'll have an estimate on it. But first I want to note that this algorithm, it doesn't guarantee that you find the optimal solution, right? Even if you start from each vertex and then select the best candidate, there's no guarantee. Moreover, there's no guarantee that you produce a good candidate. It may be very, very off. So let's just write this down. This is a greedy algorithm like Dijkstra's or Prim's or Kruskal's. It does not guarantee to produce good candidates. Well, I already mentioned that the state-of-the-art result is an algorithm which produces quickly candidates which are with error less than 50%. Right? So this is really would be too good to be producing always good candidates. I'd like to illustrate this, how it can be off. So let's consider the following graph. So I have an example here, which I call a grid punisher graph. So it has also 5 vertices. Let me draw it here. B, C, D, E. And we can use red for the weights. Two, this one is 100, this one is 5, this one is 10, 1, 2, 3, 4. Okay. I proudly call this So, given this graph, you see that some weights are reasonably small, right, between 1 and 10, but there are a couple of weights which are very large, 100. And then it turns out that from whichever vertex you start, following your grid, at the very end you are forced to take one of these two large weights. For example, if you start from vertex A, so the smallest weight is 1 going to D. Then the smallest weight available is 2 going to E. It's nice. Then going to C, we get weight 3. So far so good. But now there's only one on this vertex B, so I must go to B from C, and that's 100, unfortunately. And from B to A, coming back to A, B to A, that's 3. So this has total weight of 109. And similarly, you run the algorithm for all other vertices. I'll just write now quickly the outcomes. Starting from C, you generate this sequence, and the weight is 110. Starting from E, you get ADA, CBE, the same weight, 110. Starting from D, you get DA, CE, BD with the weight 111. And finally, if you start from B, you get DA, DE, CB with the weight 109. All of them over 100, while it is easy to check, well, not maybe so easy to find, well, it's a small graph, so you can actually just exhaust all possibilities. So either way, you can find that there is a circuit AD, C, E, B, A, whose weight is only 16. But to find that, you should look beyond grid, right? Do something to find that. So this is the optimal circuit. Its total weight is much smaller. So that was just a warning that it's known that this algorithm can produce bad results. So, so how can we know in principle, right, that whatever you generated can be very far off from the optimal, right? Before I found this with weight 16, that wasn't clear at all. Maybe any route will be forced, any circuit will be forced to take one of these large weights, 100. So to that end, we will develop now an algorithm to generate bounds. So to do that, let's consider some Hamiltonian or some Hamilton path. All right. And suppose, so it has every vertex in it. So we'll single out one vertex in the path. And then I'll call next vertex V1, V2. So the path goes like that. right? And I'm now going to split these into two parts. So cut out two edges, V2A and AV1, and then the second part will be the rest of it. So I'll just draw it again. So there can be other edges. So I cut it like this. So this is A, V2, V1, V2 again. I split it. And this long part of the cycle, of the circuit, I'll call P2. And the short part, which contains only two edges, I'll call P1. So we'd like to estimate the total weight. So weight total equals weight of P1 plus weight of P2. And so if you pick your favorite vertex, in this case I denote it by A, then you can easily estimate the weight of P1. That must be greater or equal than the sum of the two smallest weights incident with A. So sum of two smallest weights of edges incident means linked with vertex A. Then I'll denote them as W1 and W2. For example, if A is this A on this graph, then the two smallest weights available are 1 and 3. So I can call W1 to be 1 and W2 to be 3. Right? Oh, sorry, 1 and 2. So W1 equals to 1 and W2 equals to 2. Okay. So whichever are the vertices V1 and V2, the sum of the weights of those two edges cannot be smaller than the sum of the two smallest weights available. Right? Okay, so that's one found. And then to estimate the weight of the long part, P2, I do the following. I remove from the original graph the vertex A, remove from the original graph the vertex A and all edges incident to it. So call this new graph G prime. So for brevity, I'll write that G prime equals G minus the vertex A, understanding this short notation also to subtract all the edges linked to A. So I can always do that. Remove one vertex and all edges ending on it. It will be a smaller graph. Then P2 is a spanning tree in this modified graph G prime. Well, it's trivially a tree, right, because we started from a single circuit and we cut it into parts, so it's just one long path, so it's a tree, and it's spanning because it includes all the vertices except for A in it. So it's a spanning tree. Therefore, its total weight must be greater or equal than the weight of the minimal spanning tree in G prime. The weight of a minimal prime 3 and G prime, and this weight I can denote as W min. No, I had W total, W min. And this W min can be found using Prim's or Kruskal's algorithms, which are really fast. Can be found using Prim's or Kruskal's. Algorithm. So combining these two parts, we find that W total, the total weight of any Hamilton circuit, must be greater or equal than the sum W1 plus W2 plus W min. Okay. So we have a lower bound, and it's supposed to be, it is true, this bound, once found, applies to absolutely all Hamilton circuits. It would tell us that for all of them, the total weight must be greater or equal than a certain number. Therefore, if you have a candidate with a certain value, and you know that the even the minimal tree, right, will satisfy this bound. You know, the minimal tree in the worst case scenario sits right on that bound. There is a certain gap, and that gap can be estimated in percentage, and it tells you, you know, in the worst case scenario, how far off you are from the optimal, not knowing actually what the optimal is. So that's the strategy. So this, what I've just discussed, is called the lower bound algorithm. This is called the lower bound algorithm. So now I'm going to illustrate how it works on that example for which I produced two candidates, right? 24 and 23. I'll generate a lower bound. And here, just like in the nearest neighbor algorithm, first you choose the principal for each choice of vertex. So here we chose A, but any other vertex can be chosen. For each choice, I could be producing a different bound. Right? So my bounds can be more and more precise. The best bound will be the largest one. So let me illustrate how this algorithm works, starting with the vertex A. So picking the vertex A, we use the lower bound algorithm. So in the first part, I'll just find W1 and W2. So the weights available starting from A is 7, 3, 14, and 10. And the two smallest values are 3 and 7, just by inspecting the graph. The smallest weight available is 3. I'll call it W1. And the next, the smallest one is 7. So I'll call it W2. Okay. If you're not sure, you can just redraw, right, all the edges incident with A. B, C, E, and D, and then put all the weights on that. 7, 3, 14, and 10. Okay, so it's just an illustration of what we've just done. Okay, now part 2, I will remove the vertex A from the graph. Okay, I need more space because I want to keep the graph itself up there. So I'll move over here. So part 2, remove vertex 8 from the graph, right? And all the edges incident with it. And what I will get is a complete graph with 4 vertices. These vertices are B, C, E, and D. And the weights, which I read off from my original graph, are 2, 1, 12, 5, 8, and 4. So that's what I obtained by removing one vertex. And now I'm going to use Kruskal's algorithm. You can use Prim's if you like, but it's really small graph, so it's really fast to use either one of those. So use Kruskal's algorithm to find a minimum spanning tree. So using Kruskal's, I have 4 vertices, so I know I have to take only 3 edges into my minimal spanning tree. Right? Always number of vertices minus 1. And the first one, obviously, the one with the smallest weight is BD. So choice, edge, weight, as usual. So first we choose BD with weight 1. And I can mark it somehow on the graph. Then the next smallest weight available is BC with weight 2. So second choice. And 4 is the next best choice. And you see that it doesn't form a circuit. So DE of weight 4, right, completes Kruskal's algorithm. So that's a minimal spanning tree, right? Just goes around like that with 3 edges linked together into a tree. And the total weight, W min, of this minimal spanning tree is the sum 1 plus 2 plus 4. So that's equal to 7. So that was the second step in the lower bound algorithm. And the final step is just to combine the weights, the estimates we found from part 1 and part 2, just add them up to produce a lower bound. So this part 3, this gives us a lower bound, which I'll denote as W sub A, just to remember that it came from choosing the vertex A in this algorithm. And is equal to W1 plus W2 plus W min. And therefore that's 3 plus 7 plus 7. So that's 17. And this bound tells me that for absolutely all Hamilton circuits, the total weight cannot go below 17, including the optimal. Right? So whatever it is, the optimal circuit, its total weight cannot be smaller than 17. Right? So we can picture the situation on if we plot the weights on well, it's a real line, but I like to put it vertical. Just to picture this. So here is our bound, WA, which is equal to 17. And then we have a couple of candidates with weights 24 and 23. So that was candidate 1, and 23 was candidate 2. So the optimal is somewhere within this interval, between 23 and 17. We don't know exactly where it is, but it's somewhere there. The worst case scenario is that it sits exactly on the bound, on the 17. But then, in that case, so in the worst case, our error is, so it's the difference, 23 minus 17, the difference between our best candidate and the bound. And we can, assuming that optimal sits exactly on the bound in the worst case scenario, we can normalize the difference in percentage of the optimal value. So divide by 17 and multiply by 100%. And that gives me 35%. So it doesn't look great yet, right? 35% is rather large. So we can work from two directions to improve this. We can try, we only tried the nearest neighbor algorithm starting from the vertices A and B. We can try starting from other three vertices, right? And see if we can generate, with some luck, we may be able to generate a smaller weight. So that will produce for us candidates further down with smaller weights. But also, perhaps, this bound is not really where the optimal sits. So we can try to improve the bound as well. We can run the same algorithm, the lower bound algorithm I've just explained, starting with a different vertex, say with the vertex B, with vertex C, and so on. And with some luck, again, we'll find that the actual bound is higher. Right? We can find better bounds which are higher. And that will narrow the interval where the optimal can be sitting. And this narrowing can come both from decreasing the weights of the candidates and increasing the bounds. So in general, trying to illustrate what's going on the same line of real line an axis for weights. So we can have several candidates with weights depicted here. Candidate 1, candidate 2, candidate 3, candidate 4 is the best. And we can find several bounds. And the bounds, they're always below. In fact, what I see the students do many times, a typical error in applying the nearest neighbor algorithm is that the students forget to come back to the original vertex. They forget that this last edge coming back, they see, oh, all the vertices have appeared, so they stop. And without that last edge, the total weights can be much smaller. So often what happens is that they find a bound, and then they find that their candidate has the weight smaller than the bound. And this cannot happen, right? If you arrive to this last stage and you find that your candidate has the weight smaller than your bound, so it means that you made an error. Either in finding the candidate, and something is missing there, or in finding the bound, right? But that's like a really simple check to keep in mind when doing this type of problem. So the bounds are always below all the candidate weights. And we can depict them, again, if you have several bounds like this. Say bound 1, bound 2, bound 3, bound 4. So you can be labeled in any way you like, but the key thing is that to pick the largest bound, because they all apply, right? They all mean that for each Hamilton circuit, the weight must be above each of the bounds. So the strongest bound is the largest one. Means the weight must be above it. Right, and you pick the lowest candidate, so that this strip where the optimal can be sitting somewhere, you know where, but you try to make this interval as short as possible, right? And that's what people do in real life in these competitions, right? It's just they use much more sophisticated algorithms, you know, constantly improving, you know, different blocks, generating more sophisticated candidates, and also improving, you know, trying different strategies for generating bounds. And with some luck, one day you find that your candidate has the weight which coincides with the value of your best bound. That means you're bang on the optimal. So that's how they prove that what they found is actually the optimal. So there's no algorithm which guarantees that you can find the optimal, but with some luck, using this strategy, people manage to find the optimal circuits for very large graphs. Right, so this completes graph theory. Any questions at all? Regarding the meter, everything I had to say, I said in the emails. I sent it twice, right? But it's also available on Vision in the assessment folder. There's a file which explains in detail which sections will be on the meter, and you know, facts about calculator and the answer in terms of tutorial. So just read this carefully. It's supposed to answer all of your